Part 3, we're talking about DNS of ammonia hydrogen flames. And I think I showed some of this already in motivating some of the hydrogen flames. The picture on the left is just showing the temperature of an ammonia hydrogen nitrogen flame, premix flame in a turbulent mixing layer at 10 atm. And the picture on the right shows an RQL burner, which is for trying to burn rich in the first stage with ammonia and then burn lean in the second stage by adding additional dilution air in order to burn out the NOx and trying to get rid of N2O, nitrous oxide, which is a harmful CO2 gas. And I should say that the RQL second stage inverted turbulent diffusion flame was simulated at 20 bar. So we're moving up in pressure. As I said at the beginning, ammonia hydrogen has the potential to be an alternative zero carbon fuel for these hard to electrify sectors, such as long-haul marine shipping, power generation, and agriculture. It also could be used as a way to store hydrogen temporarily. But neat ammonia has low reactivity compared to natural gas, and you could improve the reactivity by adding hydrogen to ammonia or by partially cracking ammonia to form hydrogen and nitrogen with a little bit of waste heat. But the behavior, combustion behavior of these ammonia hydrogen blends is still relatively poorly understood, especially again at high pressure. So I'm going to try to touch upon 3 topics. The first one being blowout resilience. So what happens under fueling conditions and high turbulence conditions? What happens, how resilient is it to strain rate? The second and third topics deal with pressure effects and then emissions of NO and N2O. So we did some work with the CEFRC NTNU folks. Sam Weissman and James Dawson did the experiments. Martin Reith and I and Andrea did the DNS simulations. So ammonia is a synthetic fuel, hydrogen carrier. It's easy to store in big quantities as a liquid and can be burned as a liquid at engine pressures or as a gas with a tiny bit of heating. However, the flammability range, flame speed of premixed ammonia air flames is much worse than other hydrocarbon fuels like methane. And so if you partially crack it, giving a mixture of ammonia with hydrogen and nitrogen in a 3-to-1 molar ratio is a good way to improve the combustion properties. So the blends can be selected to match a lot of the laminar flame properties that are well understood for methane and propane. And so these figures on the bottom just show the adiabatic flame temperature, the laminar burning velocity, and the thermal flame thickness for the ammonia hydrogen mixture compared with methane. And so we've matched the laminar flame properties of this ammonia hydrogen blend with methane properties. So the NTNU guys did some experiments in a rig that's used to study blowout experiments. It's axisymmetric rigs. The flames are fully premixed, and the rig is open to the ambient air, so there's no confinement. These flames nominally stabilize in the recirculation zone behind the bluff body. And the reactant velocity, or the blowout velocity, is the bulk velocity from this annular injector port, defined based on the volume flow rate of the reactants, divided by the projected area of the port. And so the way that the experimentalists measured blowout limit is to ignite a stable flame, and then they slowly jacked up the air flow rate until the flame blew out, all the while keeping the fuel flow rate constant. And so this trajectory through the velocity equivalence ratio space that is shown by this solid black line in this figure on the right, showing the blowout velocity versus equivalence ratio. As the flow rate increases, the reactant velocity goes up, and the flame becomes leaner. And this process then is repeated using different fuel flows to identify the various positions in this blowout curve. And so they had optical diagnostics with OH chemiluminescence imaging at 10 kilohertz framing rate, and also OH PLIF imaging at 10 kilohertz. Then this figure here on the left shows the measured blowout curves, where the blue markers correspond to the ammonia hydrogen blend, and the black circles refer to the methane air flame. And so if you consider the equivalence ratio range where we can see blowout for both fuels, this is this gray hatched shaded region in the figure. The blowout port velocities for the ammonia blend are nearly an order of magnitude higher than for methane. And remember, as I showed at the beginning here, that the laminar flame properties were the same for the same equivalence ratio. And so this very high resistance to blow off for ammonia is a little bit surprising. We're expecting to see similar blowout conditions. Considering that the laminar properties are the same. And so normally the blowout correlation predicts blowout at a so-called critical Domkohler number, which is the ratio of the flow to chemical time scale. And in the simplest correlation, the critical Domkohler number, dA critical, is constant for a given stabilization geometry. And then the flow time is just inversely proportional to the flow velocity. And so, in other words, if you see an order of magnitude difference in the blowout speeds, that would suggest that there should be an order of magnitude difference in the chemical timescales. And these two assumptions imply that if you consider any two blowout events, the ratio of blowout velocities should equal the inverse of the ratio of their chemical timescales, as shown in the blue box. And you can define the chemical timescales in a bunch of different ways. TPF, tau PF, is based on the ratio of unstretched laminar flame thickness and flame speed as one definition. Another one might be the blowout residence time of a perfectly stirred reactor. And a third one, tau extinction, would just be taking the inverse of the extinction strain rate as your chemical time scale. But considering that blowout points, well, first here we consider the blowout points at an equivalence ratio of 0.6 as denoted by that vertical line in the figure on the left. And so for the ammonia flame blowout curve, the point is labeled A1, and for methane, labeled as M1. And again, you see an order of magnitude difference in the blowout curve, in the blowout velocity. And so if you use that blow-off criterion, the ratio of the chemical timescales between methane and ammonia would give you 1, 2.6, or 3.8 in the worst case for the three different definitions. But yet we see a blow-off ratio of close to 12. And so those definitions don't account for what we see. So to better understand what we saw and to explain it, we ran DNS of a turbulent jet in a slot configuration, a temporally evolving turbulent jet at same conditions, Reynolds number 13,800, a little bit higher, 14,800 for methane, same size, the domain and speed for both cases, very low Domkohler number for both cases. And we used ammonia hydrogen mechanism developed by Sandia with 19 species and a 16 species methane air mechanism. And this DNS flame, turbulent flame, lies in this premixed regime diagram on the right that is close to the border between the thin reaction zones regime, where the preheat zones thickened, and the broken reaction zones regime, or distributed reaction zone regime under even higher turbulence conditions. So I'm just showing you the reddish colors to yellow colors, just showing the time evolution of this temporal slot jet. So this then shows a movie of the evolution of the OH profiles in a 2D cut for the ammonia hydrogen flame on the left and the methane air flame on the right. and I'll play it again, but you can see that there's much faster flame surface generation and more wrinkling for this ammonia-hydrogen air flame, and overall stronger burning for the ammonia-hydrogen air flame, which is also, and you can see some quenched regions in the methane air flame up there on the top right, where you don't see any evidence of quenching in the ammonia-hydrogen flame. Same thing we see in the statistics. We see comparing the fuel consumption speed, flame surface density, and the stretch factor. The blue symbols are the ammonia-hydrogen flame. Methanes are shown in black, so we see a much faster increase in the flame surface density and the consumption speed for the ammonia-hydrogen air flame compared to the methane air flame. We also see that the stretch rate, which is the normalized consumption speed normalized by the flame surface area, increases nearly 2x larger than for the methane air flame, which actually initially decreases before it goes up. So what's the reason? So when we look more closely, a major contributor to the differences in the blowout curves is due, again, to the high diffusivity of hydrogen in that blend. The plots on this slide here are just for the ammonia blend DNS, and it shows the preferential diffusion of effects of hydrogen. So this plot on the left, these two plots on the left show the atomic hydrogen to nitrogen ratio, and then to the right of that plot is the OH mass fraction. And so you can see there in the reddish colors on the left, we see some locally enriched regions which coincide with high OH, high heat release rate. And these regions are superadiabatic, as we saw earlier for the hydrogen flames, which is a characteristic of flames with subunity Lewis numbers. The right two plots then show the statistics, the mean local equivalence ratio and the local heat release doubly conditioned on curvature and progress variable. And so you can see that the superadiabatic regions are seen in the positive curvatures, convex to the reactants, as we saw before for hydrogen, and are due to the local enrichment due to the focusing of the hydrogen. So we see again for this blend of ammonia and hydrogen that the overall effect of thermodiffusive instability is enhanced burning rate, which leads to this resistance to strain and then the much higher blowout velocity. So let me stop here and I'll come back tomorrow and talk about the other two topics for ammonia before moving on to staff combustion and reduced order modeling. Okay, thank you all.